Okay, so let's start. So I want to first tell you a memory, a story from my childhood. I remember when I was a kid, I, of course, liked to watch TV. And there was this TV program that I was obsessed with. I always wanted to watch this TV program. And it was going on a specific time during the day. I think it was 4 o'clock, if I remember correctly. So if I was in front of the TV at 4 o'clock, I could have watched it. If I wasn't, there was a repeat, but this repeat was, I don't know, usually in the morning, and I was in the school, so I couldn't watch it. So if I missed it, it was gone, right? At the time, I remember I went to my brother, who's older than me, and I told him that it would have been great if, when you watch TV, you could have basically decide what you want to watch. You could have just said that, yeah, I want to watch that program, and you could have watched that program. It would have been amazing. And my brother told me that, well, for that to happen, the TV company has to send a different signal to every TV set in the country so people can decide what they want to do. And because of that, that is not possible, right? And, well, I was a kid, but, I mean, the logic was simple enough. So when my brother told me this, I was like, yeah, he's right. It's not possible. That can't be done. But possibly the only things that you watched this week, which were not on demand, was the Sven talk and this talk that you're watching right now. Everything is on demand now, right? So things change, right? You know, there are lots of things that you're used to, and then those things, you know, throughout the, you know, given the technology, given the things that are happening, they are changing. So the topic of this talk is achieving cache level performance without storing data in RAM, which kind of seems like it's impossible. How can you do that? But I'm going to explain that how this can actually be done. And before we're starting that, I'm going to fire up this missile, and yeah. Well, I usually get a lot of laugh and cheers, and no, wait, no. I'm going to do it again. It's, you know, it's we want to do it justice. We want to do it justice. So when it's going up, everybody's cheering up, and you know, I wanna see the passion. Ready? 1, 2, let's go. Very good, very good. I remember I should have told you this earlier. I'm originally Iranian, so you just cheered an Iranian launching a missile. So, so be careful going back home tonight. You know, bad things might happen to you. But okay, let's talk about the topic. So, you know, computers have 2 components that can store and hold data. One of them is memory, and one of them is disk, right? So these 2 pieces of component have opposing characteristics. The most, I don't know, important one that everybody's familiar with is that RAM is very, very fast. Disk is also fast, but is not as fast as RAM. So access time to memory is usually in order of nanoseconds. It takes like a nanosecond to access disk. Disk is still very fast, but it's 1,000 or 10,000 times slower than disk. It's less than 10 microseconds, right? So nanosecond, like 1,000 times, 10,000 times slower, between 1 to 10 microseconds. So that's the speed that you get from memory. So one of them is very fast, the other one is very slow. The other one is that is the throughput. The throughput of RAM is massive, right? Usually each module of RAM that you have on a motherboard can handle something between 5 to 4 gigabytes of data per second, right? When you go to disk, 54. When you go to disk, the fastest disks that are in the market can handle around 14 gigabytes per second, but I mean, it's still a lot, but again, it's not similar to just one module of RAM being able to handle that much. If you have multiple modules, each of them are going to give you around 50 to 60 gigabyte of throughput. So again, RAM has a massive throughput. This throughput is massive as well, but significantly smaller than RAM. Then it's the price. Memory is ridiculously expensive. I mean, 128 gigabytes of RAM, one module of 128 gigabytes of RAM is something around 800 to 900 pounds. But the disk that, I just mentioned, the 14 gigabyte per second disk that you can buy on Amazon and get it next day delivery, that's around 500, 600 pounds for like 4 terabytes. So the speed is significantly different. The cost of it is significantly different. The other one is about limit of amount of RAM that you can have on a machine and the limit that you can have disk that you can have on a machine. So modules of RAM are usually very tiny, right? 128 gigabyte is usually the maximum size that you get. So these tiny modules, and then on a motherboard, you have very few slots that you can put these modules in. So you cannot have a significant amount of RAM. On, I don't know, massive computers, the most expensive computers that you can buy, you might have up to like 24 terabytes of RAM, but that's the maximum. I mean, that's not a commodity hardware anymore, right? On a massive computer, 24 terabytes would be the maximum. Usually computers have like 1 to 2 terabytes of RAM, right? So, but disk is not like that. You can very easily just add as much as disk as you want. You can very easily have like to half a petabyte of disk attached to a single machine. So again, the amount of memory you have is limited. The amount of disk you have is significantly larger. And then lastly, memory is volatile, meaning that if you lose power, the data will be gone. Disk is not volatile. If you lose power, the data is going to still, when you turn on the machine, you can still see the data. So now if you're building a data store, like a database, you have to basically decide which component of this database you are going to put on which one of these basically modules that we have, which one should store which one. So a database has to store data. So one of the places that you have to store data is, one of the things that you have to store is the data itself. So we know that data has to be persistent. And so it's obvious that the data has to be stored on disk in a database, right? So there's no other way. You have to store the data on disk. So we store the data on disk. The other component of all databases is index, or indices. So there are multiple type of indices in a database, but there is at least one. There's always one index in any database that you are familiar with. And it's the index that basically allow you to fetch the data on a random access. If you don't have that index, it's basically a file. You have to basically read everything to find the piece that you are looking for. So you have an index. This index is data structure. This data structure has to be accessed to read the data, has to be updated when you write the data. So it's changing very quickly. You have a lot of throughput. You have, a lot of access to it. You want to update it. So the common thing is that you put the index on RAM, right? The next thing is cache. So all the databases that you are familiar with has a cache, which basically keeps part of the data that is also available on disk, on RAM, to allow you faster access, higher throughput, and things on that. And we are going to talk about that in a moment, but you put the cache on memory as well. But the thing that happens here is that this index and cache, because both of them are in memory, you usually end up with a limited amount of memory. And what happens is that your index basically overflow to disk as well. So indices, basically your data structure that says that this piece of data is located on that part of disk, part of it is on RAM, but then there are some data structure on disk as well. So you cannot just read the data with one access. You have to go to the data structure on disk and still do some few searches on disk to get to the actual data. So it's the typical thing that you get from a database. So, okay. So now if we assume that this is one computer and it's made of a bunch of RAM and a bunch of disk, and we created a database on it, whenever the requests are coming in, some of these requests are going to be on RAM, which is fast and, you know, everything. And they are going to be responded very quickly from RAM. But the data that is not on RAM have to go to the disk. Then you have to come back, update the memory. So next time that you are looking at it, it's in cache, and then respond back. And because of this, usually people think that when you have a cache, it is speed up your process, right? So you put a cache, or I don't know, you add more memory to your database and you expect it to run faster, right? This is a common thing that people do. I'm pretty sure you've heard this before, you've done that before possibly. So this is a very common practice. But I want to talk about this and tell you that why I don't think that this is a good idea. So let's first talk about how you measure response time. You know, we said that, you know, cache speed up things. So let's first talk about what is the meaning of speed, right? So you cannot measure the speed of a system based on a single request. You know, so that I send a request, I receive that, the speed of the system is like that. The speed of the system is always measured across usually a large duration of time, right? So let's say you look at, I don't know, the request that the system handled during, let's say, a month, right? So now, if I make a sorted list of the duration of all of these responses, right? The duration of the time is going to look something like that. So basically, this is the shortest request that we had, and the top line is the longest request we have had, right? So the shape is always going to be something like this. Any system that you've ever seen is going to be like this. Basically, a very large portion of the requests are going to be very fast and not very different from each other, right? All of them are going to be fast and very well. But there's a small portion of the requests that are happening at the times that something bad is happening in the system. I don't know, a disk has failed, I don't know, there's a network glitch. If you're working with Java, there's a garbage collection happening. I don't know, it could be just like, I don't know, a surge of requests are coming in. So something bad is happening in the system. So if you have something like that, well, those things can happen at the same time as well. I don't know, a garbage collection happening over a network glitch, and so you end up with things like that. But all of these start to become less and less likely. So it's only a less likely situation that these things happen. You know, some systems, this less likely part is at 90th% of the request, sometimes at 99%, sometimes 99.9%. The shape is always the same, this amount, and when that's basically hockey sticks start to go up, that's depending on the system. But this is the situation. So this is how we talk about speed, not only about databases, about Kafka, about anything. It's always like this. So if you have a database, and this database, you know, the response time of the database is like this. And imagine this database doesn't have enough memory to cache any data. If the speed is like this, if I now add more RAM to this database, right? So now this database can cache more data. The thing that is going to happen to the response time is like this. Basically, a percentage of the data is going to perform significantly faster, right? And a percentage is not going to be in the RAM. You have to still go to the disk, and basically nothing changes for them. And the thing that happens is that basically your fastest queries become significantly faster, but your slower queries that basically were slow because bad things were happening don't change at all, right? So now say that, okay, so what? You know, we are making the fastest part of the queries faster. So what is going to be effect of it on, for me, as a system developer, as a project manager, as an architect, or whatever? So there are many reasons that this is a bad thing. The first one is that but it runs on my machine. Why it's not working on the production environment? So let me explain why I'm saying that this is a common thing if you are using a cache. So when you're testing your application, right, you're either running a, I don't know, Docker instance on your local machine, or maybe you are running, I don't know, a tiny server on AWS or whatever, and you are testing your application against that, right? This tiny database might have very tiny amount of resources. Maybe you just gave it 512 megabytes of RAM, right? But as long as there is a little bit of RAM there, that database can still cache data. And usually, I don't know, I've been a developer as well, don't lie to me. Most of the time when you test, you just test it with like 200 records, just see if it's working or not. And if it is working, that 200 records, all of them will be in memory. So when you test your database, you're just testing the cache, not the database, right? So you run something, it works in your simple test, you take it to, I don't know, the higher level, you take it to a staging environment and everything fails. And you're like, what is happening? So that's the discrepancy that you're introducing to your database by having a database that has a cache. But it can be even more than that. It can be that you put an application in a pre-prod environment and it's working in pre-prod environment fine, and you take it to production environment and it fails in the production environment. Why? Because, I don't know, when you were running the test was running in this specific sequence, and that the specific sequence was populating the cache in a specific way. So now you're in the production environment. Production environment population of cache is based on how the requests are coming in, and things start to fail again in the production environment. It can be even worse than that. You can have a situation that your database, your application is in production, and it's been in production for the past 10 years, and it's been working fine. And then suddenly a pandemic happens and everybody starts buying toilet papers left and right, and your caches start to get populated in a different way, and all of your applications fail. And no one knows why. I mean, solving these problems are not trivial. You know, I mean, when you have an application that its response time starts to become behaving differently, you may create deadlocks in your application. Well, there might have been some deadlocks in your applications that you never faced because the response time of one of the underlying system was like that. If you change that, your application might end up in a deadlock, and good luck finding that in production, that why something like that would happen. But I'm even gonna go further and say that, yeah, we said that it's making the fastest part of your queries faster, but I think that making fastest part of your queries faster has zero effect on the speed of your application. And let me explain more. So when you build an application is not built of one database call, right? You always make lots of calls to a database, or I don't know, several services that each of them are calling, I don't know, one or many times a database, right? So imagine you want to look at an Amazon page. In the Amazon page, you just, I don't know, you want to buy an item. There's a, I don't know, request to get the item from the database related to the item that you want to buy. There are reviews of this item. There are items that were bought with this item. Many users bought them together. There are items that are similar to this item. You know, all of these are different service calls and database calls that you have to fetch. So usually your application have lots of sub-operations. Each of these sub-operations are taking a bunch of time. The amount of time that it takes for the entire task to finish depends on the longest running task. So if this is not fast and you want to speed it up, right, you have to, well, basically do something that basically the longest running task will start to become smaller. But when you introduce a cache, it becomes something like this. It becomes like this pink thing. So many of the things start to become faster, including possibly the longest running task. They start to become faster, but not all of them are going to get faster. A percentage is going to be, I don't know if your cache hit rate percent is 70%. 70% of the sub requests are going to hit the cache and you are going to get benefit. What about the other 30%? You know, if your cache hit rate percent is 70%, if you have 2 sub operations, just 2, 70% to the power of 2 is 49%. The possibility that both of those operations are on the cache drops below 50%. You have 4, it becomes 25%. So it just exponentially goes lower and lower. So when you have a lot of sub-operations, just adding a cache has literally 0 effect on improving the performance of your application. And then, well, I mean, also consider this. Whenever you talk about performance, you are talking about 99 percentile latency, 95 percentile latency. Who cares about improving 50% latency? I mean, 50% latency, who cares about that? So, I mean, adding a cache, even with 90% hit rate, is not going to do anything. So, have that in mind. It's just adding a cache doesn't do much. So, at this point, a very good question is that, so why every database in the world has a cache? Does anybody know that? Well, it turns out that cache is actually a very good way to increase throughput, right? So, well, another missile-related joke. Just look at this. Just look at, I mean, boom. I mean, very proud of that. Anyway, so yeah, caching enhances throughput, not latency. And let me explain why I'm saying that. So remember, we saw this picture and I said that, yeah, these ones are working slowly, slower in comparison to the ones that were in the RAM. But there's something else happening here. And is that we had 10 requests coming in here and we only have, well, 12 requests coming in here, but we only have 7 requests coming to the disk. So basically this much throughput was handled by RAM, which we know can handle a lot of throughput, and just a few of the requests came to the disk. All right, so adding a cache in front of the database actually is for improving the throughput of the database, not the latency. And throughput and latency are 2 separate topics, but they can affect each other. If you start using the throughput to the max, then things have to be queued. When things start to get queued, the latency starts to be affected as well. But generally, if the system is designed correctly, you have enough resources. So adding this is only for increasing the throughput of your system, right? But there is another thing, and is that all of the databases that you're familiar with, you know, were designed in the past, well, around 20 years ago. Right? And since 20 years ago, disks that we have are around 70 times, handling around 70 times more throughput than the disks 20 years ago. Right? 20 years ago, disks could handle around 200 megabytes per second. As I said earlier, there are disks in the market that can handle 14 gigabytes per second. Right? So it's 70 times more. But you might say that, but is that really important? I mean, everything is getting faster, right? No, nothing is getting faster. That's a lie. Look at the CPUs back in 20 years ago and compare them with now. The CPUs that I had on my laptop 20 years ago was a 2.4 gigahertz CPU. The CPU that I have on my Mac today is still a 2.4 gigahertz CPU. I mean, on supercomputers, yeah, you might get 5-6 gigahertz as well, but they are rare things. You know, we are talking about commodity hardware. The speed of CPU hasn't changed in the past 20 years. We get more cores on a single CPU, but the cycle, the frequency of the CPU hasn't changed. It is almost the same for the RAM as well. We have significantly larger amount of RAM, but the speed that DDR3 can handle in comparison to DDR5 is almost twice more. So yeah, our RAMs are like handling twice more. This can handle 70 times more. So this is a significant number. We are not talking about, oh, everything is starting to become faster and the disk faster. No, disk has become significantly better in the past 20 years in comparison to the other technologies that are in the market. And it's mainly because disks used to be, I don't know, magnetic disks. Now disks that we have are working on NAND transistors. They are actually very similar. The technology is very similar to RAM. So now the idea is that, can you build a database without a caching layer, right? And if you do that, what's going to happen? And that is basically the entire idea of Aerospike. So Aerospike is a database that doesn't have a caching layer. And in the next few slides, I'm going to explain what is the meaning of that. Okay, so we said cache is part of the database always. And we said that Aerospike doesn't have a cache. So if you remove the cache from the database, we're going to free up a lot of RAM, right? If we free up a lot of RAM, now we don't need to, the data structures that we have don't need to overflow to the disk, right? So we can keep all of the data structures in RAM and just the data on disk, right? So we removed the cache and we ended up with something like this. So if we go back to this schema that we had before, it ends up being something like this. We have basically a large data structure on RAM that tells you the exact location of each piece of data on disk. So when you search for something, you go to this data structure. I showed it with a tree. It doesn't necessarily need to be a tree, but it's a data structure that is quite fast, and you can search for the data. You get to the leaf that you are looking for, and that leaf have the exact location of the data on disk. And you can go with one access to the disk, read the data that you're looking for, and you will be done with that, right? So now let's see what is the effect of this on performance. So if you have a database, it's sitting over the network. So you have three latencies that you need to look at. So first about the memory, we talked about memory. Memory's access time is in order of nanoseconds. So it takes nanoseconds to access the data on the RAM. A few microseconds, you cannot do it with just one access. You have to do few, but after a few, it's going to be in order of nanoseconds. Tens of or hundreds of nanoseconds later, you have the location on the disk. Then we said that with one access to the disk, you can read the data. Access to the disk is in order of microseconds. Different brands of disk are different, but we are talking about a few microseconds, right? It's a single-digit microsecond. You get the data. What about the latency of network? Latency of network is in order of hundreds of microseconds, right? So now you send a request, you go to RAM, you go to disk, and you send a response back. How long will it take to go through all of this? Few hundreds of microseconds, right? It's the order of this is in order of hundreds of microseconds. So now let's change the thing. So Aerospike, like many other databases, can also store data in RAM, right? So it's a very actually simple thing to do. Almost any database in the world can store the data on disk or RAM. So Aerospike can do that as well. You can basically say that, ask Aerospike to store all of the data just in RAM. So index and data, both of them in RAM. It basically becomes like a cache or an in-memory database. So if you do that, Aerospike's become exactly like a cache, exactly like Memcache, exactly like Redis or any other cache that you are familiar with. So if we do something like that, so we said access to this is in order of nanoseconds, and access to this is in order of nanoseconds as well. The latency of network is in order of hundreds of microseconds. So what would be the latency of this system? Hundreds of microseconds. So that's why I'm saying that you can build a system that is storing no data in RAM, in this system, there's no caching involved. It's just an index in RAM. But because we only access the disk once, we can provide a latency that is similar to a technology that has to store part of the data in RAM. Okay, so what is the benefit of that other than just being fast? So we saw this one, we said that the gray one was without a cache, the blue one, not without a cache, a system that is built for caching, but doesn't have enough memory to cache data. Then you increase the memory so it can cache. And then we talked about Aerospike. Performance of Aerospike is something like this. So it basically doesn't have a jump that, okay, this part of the data was cached, this part of the data is not cached. Access to all of the data actually is similar to a cache. And then, of course, as I said at the beginning, that hockey stick is the same for every single database, sorry, not database, system in the world. Any system in the world, response time is going to be like that. And Aerospike is not any different. But because Aerospike is working in a different time frame, the timeouts, the retries, and everything happens much quickly. So much quicker. So basically, we end up, even in those bad cases, Aerospike start being faster than similar technologies. Okay, so let's do a quick wrap up. So I said, the main topic here was that we now have a database that stores nothing on RAM, but it provides speed that is similar to a caching technology. So that's the first thing that we discussed. But there's one other thing. When you compare, so it was, as the previous one was about the database. It's a database that is as fast as a cache. But Aerospike as a database is a better cache than caching technologies. The reason that I'm saying that is that caching technologies, cache, the idea of cache is that if I lose the machine, the data will be lost, right? So a database in no situation should lose the data. So the amount of resiliency that is built into a database is significantly higher than the amount of resiliency built into a cache, right? So Aerospike is significantly more scalable and resilient than any cache that you've ever worked with. So you can work with Aerospike just as a database and it's going to be as fast as a cache. But if you want, you can use Aerospike as a cache and it's going to be more resilient and more scalable and as fast as a cache. So that's the second thing that we have. The other thing is that we said caching, has that bump. The cache hit rate is good. If it's not a cache hit, it's not going to be good. With Aerospike, you don't have that problem. Access to all of your data. I mean, the data that you written or read 2 seconds ago and the data that you've written or read 10 years ago, the access time to them is going to be exactly the same. All of them, order of hundreds of microseconds, right? Less than a millisecond. That's the speed that you get for across all of your data. Well, none of that is in RAM, right? You might have 10 terabytes of data and half a terabyte of RAM across, all of the nodes of the cluster. And access time is going to be as if that 10 terabyte, all of that 10 terabyte was on RAM, right? And, to store 10 terabytes of data on RAM, you don't just need 10 terabytes. It has a replication factor of 3, so you need, 30 terabytes, and you need 50% extra, so you need 60 terabytes of RAM to store 10 terabytes of data with resilience. With Aerospike, you don't need 60 terabytes of RAM. 60 terabytes of RAM is more expensive than this building, I guess. So you don't need that much RAM to store that much data. So in this talk, I only covered read. I didn't talk about write workload, right? But read and write are the same in Aerospike. I just didn't have enough time to cover both read and write, but writes are as fast as read. So the speed of read and write is the same. It doesn't matter really if your workload is read heavy or write heavy. Aerospike is going to handle all of them. And then this is a very interesting thing. So, we said that Aerospike is very fast, right? But fast in computers also means something else. The only way for an algorithm to run faster than another algorithm is that it uses fewer resources than the other one, right? Fewer CPU cycles, fewer accesses to the disk, fewer accesses to the RAM. So Aerospike, because it is fast, it is using fewer resources. So if you have a true database, one of them is Aerospike, the other one is another thing, Aerospike will be like 10 times faster and it will use 10 times fewer resources. So this is a little bit, strange. We usually used to say that, oh, something that is faster or more performant is using more resources. That's for cars, not computers. Computers, the one that is faster is using actually fewer amount of resources. And Aerospike is a proof for that. So in comparison to the other technologies, we actually use fewer amount of resources. So we end up being cheaper. We are faster and we are cheaper. And then lastly, if you're using fewer resources, these resources are using a lot of electricity that is producing emissions. Production of these resources also produces a lot of emissions. So if you can move to something that is faster and cheaper, it's also going to be more sustainable, right? If you're interested, I have a few articles that I'm going through a little bit of these topics. You can read them as well. I think one of my colleagues is going to send you these links as well. So I'm telling you, people are taking pictures. Okay, okay, you are going to receive these as well, and there are going to be some other things coming up in Aerospike as well. We have a webinar actually in a few days. One of my colleagues is going to talk about some of the use cases of Aerospike, how people like Adobe and PayPal and Crypto are handling their data using Aerospike. And with that, thank you very much. It's late. Thank you very much for listening to us.